this tutorial. Welcome to this lesson, lecture number 4, numerical methods, solutions of non-linear equations. So in this lesson, we are going to cover the following. We are going to classify methods of solving non-linear equations, analytic solutions, determine analytic solutions, plot graphical solutions of equations, and then perform numerical methods solving non-linear equations. We also look at bracketing methods and open methods, and lastly we will check convergence notation. All right, so finding a root when you're given a polynomial or a function f of x, and then a root is a value such that f of that value is equals to 0. So if f of r is 0, then it means that r is a root. And if you are asked to find this solution, we call these problems root finding problems. For example, the number of r that satisfies an equation is called a root of the equation. So given the equation x to the power 4 minus 3x cubed minus 7x squared plus 15x is equals to minus 18, this polynomial has got 4 roots because the degree of this polynomial, the highest degree of this polynomial is 4. So it has got 4 roots. You can check these ones. If you substitute by minus 2, 3, 3, minus 1, all of these will give you a 0. Same when you want to use this expression and express it in terms of roots, you'll express it as factors. So the first root will give you x plus 1. The second will give you x minus 3 squared since they are repeated. Last one will be x plus 1. So the equation has got two simple roots, minus 1 and minus 2, and a repeated root 3, which is multiple of 2. Zero of a function. So what is zero of a function? Zero of a function is that any number such that if you substitute in place of f in a function, that will give you a 0. So that's the zero. That's the zero of a function. For example, if you are given f of x is equals to x minus 2, x minus 1. So the zero of a function is 2 and 3. So you equate this to 0. So if you are given x minus 2 is equals to 0, this will give you x is equals to 2, or x minus 3 is equals to 0. So this will give you x is equals to 3. The graphical interpretation of zeros. So the graphical interpretation of zeros is as follows. So a root of a function is the x value where the graph will cut the x-axis. So those are your roots. So you have got this root and then you have got this root. So these roots simply tell us where the function will cut or will intersect with the x-axis. Right, so take note of this one where the function just touches the x-axis and then go back on the same side of the axis, which is the positive. In this case, these ones will be your repeated roots. So in case of repeated root, the function will not totally cross, but it will just touch, and then the x-axis will be a tangent like that. So this simply implies that the root is repeated. Let's look into the following example. Oh, my machine is frozen. Just wait a moment. Okay, we are back. So if you are given a function f of x which is equals to x plus 1, x minus 2, this means that your zeros are at x minus 1 and x is equals to 2. So this means that this function will cut, this graph will cut at x minus 1 and x2 like that. Take note, if we expand this bracket, we will get this value, the coefficient of x squared, to be positive. Hence, the curve will be cup shaped. It will be opening upwards like this. If the coefficient of x squared is negative, then you have got an opening downwards. So the curve will be like that. The curve, if this value is negative, the curve will look like this. It will be facing downwards. So the curve will be facing downwards. So for the negative case, for the negative case, the curve will be facing downwards. Sorry for using that weird diagram, but it will be facing for positive, it will be facing upwards like that. Just wanted to illustrate so that you visualize what I'm talking about. So again, so if you are given a function x minus 1 squared, this one will give you your zeros at x is equals to 1, and this is a repeated root, and the coefficient of x squared is positive. So the graph is facing upwards and it touches at 1. Because this is a repeated root, it does not totally cut the x-axis. For the graph of x cubed, remember the general curve for x cubed looked like this. So this one has got a zeros at x is equals to 0. So at x is it, so this graph will cut at x is equals to 0 like that. So let's summarize the facts. So any nth order polynomial has exactly n zeros. So if you are given a second order polynomial, it has got 2 zeros. So any polynomial with an odd order has at least one real zero. So odd numbers, remember your odd numbers 3, 5, 7, 11, and so on, 9. So all those polynomials with those degrees has at least one real zero. If a function has got a zero at x is equals to r with multiplicity m, then the function and its first m minus 1 derivative have got a 0 at x is equals to r, and the mth derivative of r is not a 0. All right, so let's look into this one. So for example, if you are given this equation, this one has got order 4. So we expect this equation to have 4 zeros. So moving all terms to one side, you'll get this. Therefore, we define f of x as x squared minus 3x cubed minus 7x squared plus 15x plus 18. The zeros of f of x are the same as the roots of the equation. So when we are looking for the zeros of this function, we are looking for the roots of the equation. So we are simply equating f of x to 0. And these roots are minus 2, 3, 3, and minus 1 from our previous example. In detail, whenever you are finding these roots, you can either use trial and error method. So I'll encourage you to go and look into trial and error method for solving this, and also the long division method for finding other roots and other factors. Please go through that. I'll also give you questions on that. And then solution methods. Several ways to solve nonlinear equations include the analytic solutions, so possible for special equations only. And then you've got the graphical solutions for providing initial case for another method, and then you've got the numerical solutions. These are divided into two: the open methods and the bracketing methods. So the analytic solutions uses analytic methods. So for these ones, if you are given x squared plus bx plus c, this one you can use the quadratic formula. However, if you are given x minus e to the x is equals to 0, this one has got no analytic solution. That's where the numerical method helps you, or the graphical method. So the graphical method is the pictorial view of your problem. It provides you with the initial guess of the solution. Not necessarily accurate, but sometimes it gives you a guess. For example, if you are given x minus e to the x, you can move e to the x the other side of the equation and sketch these two equations. And then the first equation, e to x, will be represented by the red curve. X will be represented by this purple line. Then you can clearly see that the solutions lies within the interval 0 and 1. So your solution, you expect your solution to be somewhere the 0.8, 0.6, 0.5, somewhere there, approximate. So this will give you a guess as the graphical method. And then the numerical methods are divided into three parts for solving non-linear equations. We have got the bisection method, the Newton's method, and the second method. and these will be covered in this course. And these other ones will not be covered. So the bracketing method. In bracketing method, we start with the interval that contains the root, and then a procedure is used to obtain a similar interval containing the root. So a bracket method, you have got an interval containing the root, you apply a procedure, you get another interval containing the root. So it's about intervals with the root inside that we are interested in finding. Examples of bracketing methods include bisection method, force position method, methods. In the open method, the method starts with one or more initial guess points. In each iteration, a new guess of the root is obtained. So open method uses uses points, while this bracketing method uses interval, and these open methods are more efficient as compared to bracketing method. However, sometimes these methods may not converge. So we would want all these methods to converge, because if a method does not converge, then it means that it varies and it changes, and then it becomes difficult for us to estimate the solution. But if a method converges to a point, then it means that we can monitor and minimize errors and so on. So the convergence notation, a sequence x1, x2 up until xn, is said to converge to x if to every epsilon greater than 0. So if I can pick any value greater than 0, say 0.01, they exist n such that x minus the value of convergence is less than epsilon. So this is the notation of convergence. So if you are given x1 up to infinity and then convergence to x, you have got linear convergence, which is given by xn plus 1 minus x over xn minus x should be less than or equal to c. Quadratic convergence, xn plus 1 minus x over xn minus x, everything squared, and then we have got, this is quadratic, because quadratic, you've got order 2, and then you have got convergence of order p, and then everything is similar. The only difference is the powers on your denominator. This is linear, it has got power 1. This is quadratic 2, and then for order 3 you expect this one to be 3 also, and so on. So in summary, the speed of convergence, we can compare different methods in terms of their convergence rate. Quadratic convergence is faster than linear convergence. A method with a convergence order q converges faster than a method with a convergence order p, only if q is greater than p. Method of convergence order p greater than 1 are said to have superlinear convergence. Thank you. Hope to see you in the next lecture.